Okay, good day. This is Math 140 College Algebra. I'm Professor McCulley. This is lesson 3.2 on factoring quadratics. Let's get right to it. Okay, so today we're going to factor quadratics using common factor, difference of squares, perfect squares, and a rational root theorem, or at least a version of that. So, first thing we want to talk about is the principle of zero products. Given a times b is equal to 0, then we can assume that either a is equal to 0 or b is equal to 0. This is the power of factoring, and which we will be getting into eventually, is that if you can prove or find a value that makes this a factor 0, then it doesn't matter what b is, the whole thing will be equal to 0. So, this can be extended to if you said a times b times c is equal to 0, then a, b, or c must equal 0. And so if you have any list of products that equal to 0, then at least one of those values must be equal to 0. So what can we do? We can talk about factoring in this particular term, and factoring a quadratic expression. A quadratic expression is a polynomial expression of degree 2 that has the form ax squared plus bx plus c with a not equal to 0, because if a was equal to 0, this term would be gone, and then it would be a linear expression and not a quadratic expression. You can have a common factor, so if you have abx squared plus acx plus ad, then this thing can be factored into a times the quantity bx squared plus cx plus d, and we'll do an example of that. You can have a difference of squares, and this is the one that you'll see most often. In fact, we did use a difference of squares as a useful property for turning complex numbers into real numbers in the last lesson. So if you have a squared minus b squared, then that is always going to be equal to a minus b times a plus b, and we'll see an example of that. And then there are perfect squares. If you have a squared plus 2ab plus b squared, then that thing can be rewritten as the quantity a plus b squared. And then if you have a squared minus 2ab plus b squared, then that can be rewritten as the quantity a minus b squared. And then a rational root theorem for quadratics. If you're asked to factor something that looks like this, what you can do is you can multiply a and c, and then the correct factors of AC must sum up to B, and what we can do is that we can then rewrite the quadratic so that the factors of AC are going to replace BX, and then we will group and factor like terms, and I'll show an example of what I mean by that here very shortly. So, talking about some examples of this factor expression by using the greatest common factor. So this is still a quadratic expression, even though it does not have a constant term. It does have a quadratic term and a linear term. And so I look and I say, what is the greatest common factor to 3x squared and 9x? And clearly 3x is the greatest common factor between both of those. And when I divide 3x out of 3x squared, I'm left with just x. And when I divide 3x out of 9x, I'm left with just 3. And that is completely factored because I can't do anything else. Next, factor by using a difference of squares. And so this thing is of the form a squared minus b squared. And we can say that a squared is equal to 9x squared. So what we want to do is we want to figure out what a is. So if I take the square root of 9x squared, what times itself is 9x squared, and clearly that's going to be 3x. And we could do the same thing with b. b squared is 16, so what times itself is going to be 16? Well, that clearly is 4. And so since ax, or a squared minus b squared, is equal to a minus b times a plus b, we can say that this thing is going to be equal to, well, a minus b will be 3x minus 4, and a plus b will be 3x plus 4. We have that. Okay. rational root theorem for quadratics. Use the rational root theorem to factor this. And so usually when I have a leading coefficient of 1, I don't do that. But in this particular case, a times c is going to be 1 times -4. And that ends up being -4. And so I need two factors of -4 that add up to 3x. And clearly 1 plus -4 does equal -3. So I'm going to rewrite this with these factors in it in terms of this 3x. So I've got x squared plus x minus 4x minus 4. So I took these two factors right here and I rewrote them as 1x minus 4x. And x minus 4x does equal -3x, so I haven't changed that. And now I'm going to group. So I've got x squared plus x. And then when I group the second one with a minus symbol in between, because I'm grouping them, that means I'm subtracting away the whole group. That means I have to change both of these terms. So that'll give me 4x plus 4. And again, when I distribute that negative, I'll get back my negative at 4x and -4. And so now I want to factor each group. And that'll give me x. Let's see, the greatest common factor between x squared and x is just x. That'll give me x plus 1. And what is the greatest common factor between these two? It'll be 4. And that'll give me x plus 1. And since the x plus 1s are the same, we're going to factor x plus 1 from each of those two terms. And that'll leave us with x plus 1 times x minus 4, and that is our factoring. Same thing here. AC in this case is going to be 2 times -6, and that'll give me -12. And so I need two factors of -12 that add up to positive 1. And so 4 plus -3 does add up to positive 1. And so I can rewrite this expression as 2x squared plus 4x minus 3x, again using those factors to replace the x term, and 4x minus 3x is just going to be x, and I have my -6. Now I'm going to group these things. And if I could spell correctly, we could do that. And that'll give me 2x squared plus 4x. And again, because I have that negative symbol, when I group these, I have to change both signs. So it'll give me 3x plus 6. And then I'm going to GCF each group. It really should be find the GCF of each group, but I'm doing shorthand here. So, and the greatest common factor of 2x squared plus 4x is going to be 2x. And when I divide 2x squared by 2x, I'm going to get x. And when I divide 4x by 2x, I'm going to get 2. And then the greatest common factor of 3x and 6 is going to be 3. That'll leave me x and 2 again, and that's good because we have the x plus 2 and the x plus 2. We need those two to be the same, and so we are going to factor x plus 2. And that'll give me x plus 2, and what's left will be 2x minus 3. 2x minus 3, and that is my complete factorization for that. And that's all I have for today, folks. That one's a pretty quick one, only 9 minutes. And so the Marvel fun fact of the day: in Spider-Man Into the Spider-Verse, Kingpin is modeled after the Kingpin in Daredevil War and Love and War, which is a 1986 graphic novel by Frank Miller and Bill Sienkiewicz. I know it doesn't look like that's how you pronounce it, but apparently that's right. Bill Sienkiewicz, a very unique comic book artist. Well, that's all I got for today, folks. Have a good day. Bye.